My name is Krista Bowers. I'm the lead of Team Volgemobile, which is a team of 6 mechanical engineering students and 3 computer science students working on the Autonomous and Conventional Vehicles for Disabled Riders project. The project sponsor is 4VA Foundation, and our faculty advisor is Dr. Moran. Approximately 15% of American adults are deaf or hard of hearing. Team Volgemobile was tasked with developing a suite of technical modifications to enhance the use of autonomous and conventional vehicles for deaf or hard of hearing drivers. To ensure that we were in constant communication with our customers and learning about their pain points, we conducted 18 different customer discovery interviews, which revealed that the #1 challenge faced by deaf or hard of hearing drivers is identifying emergency vehicles, as shown in Figure 1. During the fall 2022 semester, we developed 3 alternative designs for our final prototype. In all of these designs, they consist of a sound recognition system and a haptic alert system. In design 1, we would utilize a haptic seat cushion, a haptic steering wheel, a sound recognition system consisting of a machine learning model trained using an Urban Sound 8K dataset, Android mobile app, and 4 microphones, with the computer hardware of a Jetson NX Xavier. In design 2, the seat cushion would only utilize 2 motors. We'd have a haptic steering wheel. The sound recognition system would include a machine learning model trained using a custom dataset, the Android mobile app, and the 4 microphones, and the selected computer hardware will be an Intel NUC 11 Pro. In design number 3, there would only be a haptic seat cushion, and the sound recognition system would consist of a continuation of the previous Capstone team's machine learning model, a web-based application, and the 4 microphones. And the selected computer hardware would be a Raspberry Pi 4 and a Dell laptop. In the rightmost column are the haptic alert system diagrams. If a sound is detected in the front of the vehicle, which is simulated by a golf cart for our project, the corresponding quadrant listed will vibrate. For our final design, our power supply is a 7-watt Bluetti power supply powered and recharged by 400-watt solar panels. The selected computer hardware was a Jetson Xavier NX. The sound recognition system was 4 Razer Seren Elite microphones, a convolutional neural network machine learning model, Android mobile app, and the haptic alert system consists of a haptic seat cushion and haptic steering wheel. In the final design, the sound recognition system takes an audio input from the microphones, determines which microphone has the loudest, highest amplitude, and it's converted to a ML spectrogram. This spectrogram is sent to the ML model, and if it's detected that this spectrogram has a siren pattern, then the appropriate alerts are sent to the Android mobile app and haptic alert system. For the final design for the seat cushion, we integrated the motors into the bench of the golf cart for the user's safety. It's composed of 2 DC 24-volt 8,000 RPM vibration motors, which are housed in a custom 3D printed motor housing frame shown in Figure 5 in the top right image, and a single motor driver along with the necessary wiring, which is shown in the wiring diagram in the bottom right. We leverage pulse width modulation technique to control the vibration intensity of the motors. For the haptic steering wheel, we developed a motor harness that would be placed into a golf cart's steering wheel cover. It consists of 8 coin vibration motors with custom 3D printed ribs, foam substrate to prevent vibration spillover, 2 motor drivers, and 2 LED lights, and the necessary wiring, again shown in the figures on the right. The LED lights serve as an additional visual alert as the Android app. This is a diagram of the full prototype. The microphones go on the top of the golf cart. An Android tablet will show the Android app on the windshield, and the circle with F denotes the seat cushion's location, and G shows the external power source. In spring 2023 semester, the mechanical team developed the haptic seat cushion. We developed a Python script and wired the haptic seat cushion to run using the Jetson Xavier NX. We also conducted validation testing and finite element analysis on the seat cushion to ensure it can endure the weight of a driver. We conducted motor testing by supplying varying levels of voltage, and we're able to determine the RPM and the average speed from that. For the haptic steering wheel, we developed the entire motor harness. We wired all of the 8 coin motors to vibrate each side of the steering wheel and the 2 LEDs. We also conducted validation testing and FEA on the plastic rib that would hold the motor.
Okay, 04.
For the sound recognition system, the computer science team coded a script to record sounds using the microphones and pass this information throughout the system. They trained the ML model to detect a siren sound, and they developed an Android mobile app to display the necessary alerts. On the figure on the left, you can see a mass spectrogram of a siren pattern and classification happening. And on the figure on the right, you can see the Android mobile app. To conclude, the sound recognition system developed by the CS team detects a siren in its direction. Instructions are then sent to the haptic alert system to vibrate the corresponding direction of the siren, and the alert is also sent to the Android mobile app. For future work, teams should increase the precision of the machine learning model, expand the number of sounds identified by this model, and ensure that the prototype works while the vehicle is in motion. Thank you. And our project would not have been possible without our sponsors, 4VA Foundation, technical advisor, Dr. Moran, our academic advisors, and Mr. Hall, Ms. Calick, Professor Berg, and Michael Mullins. Thank you so much for your help, and these are our references.